Okay, so recall the definition or construction for the isogonal of a point P in a triangle ABC. What you typically think of is the three angular bisectors. They go through the incenter of the triangle, and then you take each one of the covariants through P. So I'm going to connect A to P and reflect that on the A bisector, getting that pink dashed line there. That's going to be one of my construction lines. And I'm going to repeat that for B. I can connect B with P, then reflect that about the B bisector, and I get this second pink line. They're going to meet at a point here. And then if you do the same construction by reflecting the C Cevian, where is that? Here's a C Cevian. If I reflect this one about the C bisector, I get this third pink line. And these three lines concur at what is called the isogonal conjugate of P. Now I was intrigued, and we've used this on a recent paper, this equivalent construction that in a way looks simpler, and you're going to see why I'm mentioning it. The isogonal conjugate of P, which is this point P dagger over here, is simply a reflection on the center of a special circle, this pink circle. What is this pink circle? From P, you just drop the perpendiculars to each one of the sides of ABC. So you're going to get the feet of the perpendiculars as PA, PB, PC. These are also known as the vertices of the pedal triangle of P, or the P pedal. Now, there are 3 points. You can certainly draw a circle through these 3 points. You can calculate its center O, and then the isogonal is simply given by the reflection of P on O. So you get it over here. Now, because isogonality, or isogonal conjugation, is an involution, the feet of the pedal of P dagger, of the isogonal of P, are also going to lie on the same circle. Now here I'm using P dagger to represent the isogonal, but in the following discussion I'm going to use little g, big P to represent the same thing. Now, why am I showing you guys this circle-based construction? Very simple reason. It allows me to do a very elegant generalization of this of the isogonal conjugation to 3D. Okay, so let's take a tetrahedron shown here in brown. Okay, and without loss of generality, the particular tetrahedron I'm showing here, I believe, is I would have to check that. Yeah, it's a regular tetrahedron. Okay, but that's without loss of generality. So I got the tetrahedron here. Let me just zoom in a little bit, zoom out a bit. Am I centered on my? I'm always worried that I'm not centered on my video. Looks like I'm more centered now. Okay. Now, how am I going to define the isogonal conjugate of a point P, whose coordinates px, py, pz I can place anywhere on the plane? It can be interior or exterior to the tetrahedron. Okay. So here's what I'm going to do. I'm going to drop 4 perpendiculars from P onto the 4 sides of this tetrahedron. And their feet are being shown here as these little blue dots. So these lines are, for example, this line here is a perpendicular drop from P onto that bottom side. This one over here is dropped on the left side, and so forth and so on. Okay? I think this is a better rendition of the 3D scene here. So you can see that there's a perpendicular here and a perpendicular there. So what I can do next is I have 4 feet of perpendiculars. That defines a sphere in 3 dimensions. Right? Because a sphere in 3 dimensions is given by the 3 coordinates of its center, x, y, z, and the radius. So there are 4 degrees of freedom. If I impose that this sphere has to go through 4 points, I have a unique solution, and I'm drawing this unique solution here as this green sphere. I can certainly compute algebraically its center. Here's the center O, and all I'm going to do is I'm going to reflect P upon O to get a point in 3D, which I'm calling here GP. This is equivalent to the construction that we just looked at in 2D. Okay, go from P reflected upon the center of a circle, and I go to the P dagger, or GP, over here. Okay, so you can see here that like in the previous picture, the feet of the 4 perpendiculars dropped from the isogonal conjugate onto the sides of this tetrahedron also lie on that green sphere here in the middle. Okay, so you get this involution property done as before. Okay, so let me move P around, and you can see here that my GP moves around in 3 space. Now I'm moving, my isogonal conjugate in 3 space. Let's go to the outside of the tetrahedron, And just like in the case of isogonal conjugation, if a point lies outside of a triangle, its isogonal conjugate will also lie outside. So you're getting the same phenomenon here. Okay, and when P is interior, the isogonal becomes interior. Okay, so I'm going to use this in the next video, but let me go ahead and upload this. So this is not an overly long video. I just wanted to show you guys how I'm actually doing isogonal conjugation in a, you could call it a synthetic way. It's a semi-algebraic way because I'm using an algebraic method to compute O once I get the sphere that goes through it. Okay, I believe I am, but that's not germane. All that is germane is the apparent validity of this construction. Okay, so the isogonal conjugate of a point P with respect to a not necessarily regular tetrahedron based on the sphere that passes through the feet of the four perpendiculars drop from P onto the sides of the tetrahedron, and then a simple reflection across O to get GP. I'll see you on the next video.